Alright, so in this video, we're going to take a first look at our first non-homogeneous second-order equation, where instead of having a 0 on the right side of our equation, we have some function, or otherwise known as some g of t. And the first method of solving a non-homogeneous ordinary differential equation is called undetermined coefficients. So in this video, I'm going to detail how to start undetermined coefficients and then set up the particular solution using educated guessing. I don't know, you're thinking, I have to guess? Well, there's a pretty systematic approach to this guessing. It's not just random. So, like I said, before we had something that looked like this, right? So before we had ay double prime plus by prime plus c of y is equal to 0, right? Because our g of t was equal to 0. This was homogeneous. Now we have a non-homogeneous equation, so we're going to have a function. And just like before, a, b, and c are constant coefficients. So now, for the method of undetermined coefficients, the first step is to solve the homogeneous equation for the general solution, otherwise called y sub h. This step is the same thing that we've been doing all throughout homogeneous differential equation, second-order differential equations. We're going to use all the same methods, all the same things, except now the only difference is we're now going to call our general solution for that y sub h. And then the second step is we're going to propose a particular solution called y sub p. And this is something that's new, so we're going to look at that in this video. Now, just really quick, we're not going to look at these next steps in this video because I think step 2 is going to be enough for this one. Step 3 and 4 would be to solve for the coefficients that our particular solution, that's in our particular solution, and then we write out our new general solution, where we're going to have y sub h plus our particular solution. So anyways, we'll look at those two in the next video. For now, let's look at step 1 and step 2. But before we get into this, for step 2, there's a method of guessing for this, depending on what our g of t is. G of t can be many different functions. It can be a number like 3, it could be a t, it can be an e to something, it can be e to something t, it can be sine of something or cosine. Any other trig functions besides sine and cosine would be later used for variation of parameters. That's the variation of parameters is the second method of non-homogeneous equations. This undetermined coefficients is the first method. In the next section will be a variation of parameters. So undetermined coefficients only deals with sine and cosine. So, based on what our g of t is, we're going to have to make different guesses. So if our g of t is just, we have a numerical value in our g of t somewhere, well then, we would propose our y of p would be some variable, some coefficient, and we'll just call it a. If we have some t or some t plus 3, then that is known as a first degree polynomial. It can be either or. So this can be written as a first degree polynomial. So a plus a sub 1 of t. This is a first degree polynomial, right? Think of it, we have t to the 1, t to the 1 plus 3. This can be grouped like this, and whatever. So that can be written as a plus a1t. Doesn't matter what constant you use, but it's typical that you just follow the alphabet when you propose this. And you'll see what I mean in 1 minute. So if we have t squared, and this is what I mean, you're going to see what I mean right now actually. We're going to write a second degree polynomial. Oh, never mind. We're still only going to deal with a's here. Second degree polynomial, we'd go up to a2, where we're going to have a t squared. For a third degree, same thing, a plus a1 of t plus a2 t squared plus a sub 3 t cubed, and so forth. Same thing for t to the 4th, t to the 5th, and so on. That would be a nightmare to solve. Anything above cubed, honestly, would be a nightmare to solve algebraically. If we ever have an e to something, right, we would write that as just write out a constant in front of it. And that's it. Doesn't matter what's up here. I just chose 3 for this example. Whenever we have a sine of 3 of t, you're going to rewrite the same thing with a coefficient. And now we're just going to follow the alphabet. So we're going to go to b. And now whenever you have a sine, it has to go with a cosine. So we're going to add a cosine term to the sine term. Now there's some mathematical reasoning behind this. I completely forget. This was a year ago when I learned this. Completely forget what that was. But anyways, this is how this would go. And then same thing for cosine. You just rewrite the cosine with the new coefficient. And then plus b. And this time we have to write down a sine to go along with the cosine. Same thing. So these both are exactly the same. These both are exactly the same. Now, what if we have some kind of thing like this? If this was a 3, this would be a third degree polynomial. But because this is minus e to the 3t, it's different. It's a third degree polynomial minus this, right? So it's two different things at once. Now, whenever you have a subtraction sign or an addition sign, you're always going to take it as positive. When you write your particular solution, it's always going to be positive. You're never going to have a negative in your particular solution. So when you do this, this would be a third degree polynomial. So we're going to have, let me do this in red, just a plus a1 times t plus a2 times t plus a3 times t cubed. Sorry, this should be squared. And then we have plus, right? It's always positive, plus b e to the 3t. Okay, that's how that would work. Now, what if we have multiplication? Well, so you simply just multiply. T represents a first degree polynomial, so a plus a sub 1 of t times sine of t. But now remember, sine of t has to go with a cosine. So plus, we're going to write the same thing again. This time we're going to have b plus b sub 1 of t times cosine of t. Okay, so I recommend taking a screenshot of this, and when we do the first problem, refer back to it, right? I think this is pretty much every case. We might have missed one or two, but we will definitely see them in the next few example problems. I believe I have 5 examples to show you. Also, quick note, if any term in our y of p matches a term from our y sub h, then we're going to multiply that term in y sub p by t. And what do I mean by that? Well, here's an example. Say our y sub h is c1 e to the 2t plus c2 t e to the 2t. So if you remember, this kind of, I chose this because you'll see why. But this resulted from a repeated root. Remember, then you do either the shortcut method or reduction of order to get this t here. But anyways, and then what if our y sub p was this whole thing? This term plus this term plus this term. Well, what you have to do is you have to look at this term and this term from our y sub h, and this term, and this term from our y sub p, and see if any of them match. So now remember, for this, we don't group this and this separately. We group them together. The coefficients are separate from this. Coefficients are separate from this. Coefficient terms are separate from this. Okay? Do any of them match? You're going to say yes, right? These two don't, so let's get rid of these. Does this match with any of these? Yes, this one matches with this one. So what this means is you're going to multiply that term in y sub p by a t. So we're just going to add a t right to here. Now let's look at this again. We still have to check again. Does this match anything that's up here? And you can see now why I chose this example, because yes, it does, right? If it does again, then you just simply add another t. You just multiply by another t, so it becomes t squared. And that's just another thing to keep in mind when we go through this. Okay, so next, example 1. So example 1, it says, propose the right form of a particular solution of the equation. Do not find the coefficients. So that means just to do step 1 and 2 that I wrote up here. So we're going to solve the homogeneous equation for the general solution, y sub h, and propose a particular solution, y sub p. So, what does solve the homogeneous equation mean? Well, that's what we've been doing all along in second order differential equations. All we're going to do is we need to solve for our y sub h. This is what we want. And we know that we have to solve it homogeneously, so our g of t would be equal to 0. So what does that mean? Well, that means that y double prime plus 9y is equal to 0. Okay? And we solve this just like how we've been. We propose y is e to the rt. Plug them in. Take the first, second derivative. Plug them in. Cancel out the e to the rt's. We should be very familiar with this by now. We're left with this. Well, this looks like it's going to be complex, right? So then r is equal to what? The square root of negative 9. Let me come up here now. So then r is equal to plus or minus, this should be plus or minus, 0 plus or minus 3i, right? Now remember that little shortcut I showed for complex to work around using the Euler formula was to do c1 e to the 0 t times either sine or cosine, doesn't matter which is first, times cosine, if this 3 goes here, 3t, plus c2 e to the 0t times sine of 3t. Now, of course, these are just 1, so y is equal to c1, because remember, e to the 0 is 1, plus sine of 3t. Oops, I forgot the c2 here. Okay, so now this is our y sub h, right? Sorry, I should have wrote y sub h. This we were familiar with. We've been doing this for a little while now. That was step 1. Step 2. Solve for y sub p. So now remember, y sub p requires some educated guessing. So our g of t in this case is 2t cosine and 3t. Now remember, our guessing was dependent on our g of t. So our y sub p would then be equal to, we had an example just like this, right? We have a t times a cosine. So t represents a first degree polynomial. So a plus a sub 1 of t times cosine of 3t. And now remember, a sine has to go with a cosine. So we're going to have plus another first degree polynomial times sine of 3t. Right? So this is almost the correct particular solution. But don't forget, we have to double check. Does this or this match this or this? You're going to say yes, right? They both match something that's up there. So then we have to add a t. And then we check again. Does this or this match anything up there? Nope. So then this is our final answer right here. This is our y sub p. This is what it asked for, right? Pretty simple, pretty straightforward, right? We have 4 more examples to go through. Okay, now remember, step 1, y sub h. Oh, example 2, right? Example 2, y sub h is equal to what? Step 1, y sub h is equal to what? That's what we're solving for, where g of t is equal to 0. So y double prime minus 5y prime plus 6y is equal to 0. Propose e to the rt, plug them in, cancel out the e to the rt's. R squared minus 5r plus 6 is equal to 0. I think this factors nicely. R plus 3, R minus 3 times R minus 2. Yep. So then R is equal to 3 or 2. So then our y sub h would be, I'm doing this part really fast because we should be pretty familiar with this. C1e to the 3t plus C2e to the 2t. If you have any trouble with this part, please go back to my previous second order videos and watch those. Where was I? Let me check this one. C1 2e to the 2t and 3t. Yep. Okay, now let's look at the particular solution. Step 2. Y sub p is equal to what? And our g of t, that's given. Oh, great heavens. Et cosine of 2t plus e to the 2t times 3t plus 4 times sine of t. And I encourage you to go through, pause the video, try to propose it yourself. And then I'm going to do it and see if you get it right. Okay, so let's see. We have an e to the t cosine of 2t. So we're going to have a coefficient times e to the t times cosine of 2t. Now remember, cosine has to go with sine, so plus b e to the t sine of 2t plus, we have a first degree polynomial. I'm going to write that part out front. The 3t plus 4 is a first degree polynomial. So I'm going to write this out as, we're on to c now, right? Follow the alphabet. C plus c1t times e to the 2t. I just rearranged those two, times sine of t. Plus, sine has to go with cosine. Now we're on to d. Plus d1 of t, e to the 2t cosine of t. Now let me just double check. Oh, before we continue, I almost forgot. Do these match any of these? Looking at them, I don't think so, right? So I believe this is our final answer right here. Let me double check. Yep. And yes. Okay, yep, this is correct. So hopefully you got this part, you got it right as well, right? So now let's go to the next one. Let me move this up. Example 3. So that's a pretty long g of t, right? Well, step 1, solve the homogeneous equation. Now this would just represent, remember, propose e to the rt, y equals e to the rt. Take the first, second derivative, plug them in, cancel the e to the rt's. We're left with r squared plus 4r plus 5 is equal to 0. Can this factor nicely? I think so. No, I don't think so actually. Nope, it does not. We have to use the quadratic formula. So r is equal to minus 4 plus or minus the square root. 4 squared is 16 minus 4 times a, which is 1, times c is 5, over 2. I'm going to bring this up here. R is equal to negative 2 plus or minus. That is 16 minus 20, negative 4 over 2. Square root of negative 4 over 2. Negative 2 plus or minus, that's 2i. 2 divided by 2 is 1, so just I. So that r is either equal to negative 2 plus I or negative 2 minus I. I don't need to write that, right? Ry sub h, we have complex, right? So c1 e to the negative 2t times cosine of t. Remember the shortcut? This goes here, and this goes here. Plus, it doesn't matter which, if you write sine or cosine first. Sine of t, right? So that's our y sub h. Now, step 2. Propose our y sub p, right? So, our g of t is very long for this one. I'm just going to go ahead and zoom out so we can see it up here. So, y sub p would be, so we have 2t. Now, that's a first degree polynomial right there. So that would be a plus a sub 1 of t. Now we have t e to the negative 2t. We have a first degree polynomial times e to the negative 2t. And then we have plus 5 sine of t. So we have a sine, so abc, sine of t, plus d cosine of t. Now the next term, we have negative 3t e to the negative 2t sine of t. We have 3t would be a first degree polynomial. So plus, we're on a, b, c, d, e, plus e t, e to the 1t, right, times e to the negative 2t times sine of t, plus f plus f1 of t times e to the negative 2t times cosine of t. And then, let's check. Do any of these match any of these? By the way, it does matter that there's nothing on the outside of this one. For example, if we had C1 by itself at the top, you can pretend there's an imaginary 1 there, right? If we just had like C1 times 1, for example, this would be repeated with what's up there. Right? But let's look here. Do any of these match? I think so, right? Both of those match what's up there. Yep, just these two right here, right? So we get rid of these. That matches with those. So we're going to add a t to both of these terms. That's a t, by the way. Okay. And then do they match any of those? I don't think so, right? So then this is our final solution. Okay. Example 4. We're moving pretty fast, right? If you have any questions, please leave a comment. And I'll get to it as soon as possible. Okay, step 1. Y double prime minus 4y prime is equal to 0. Oh, I missed a term. This would be propose e to the RT, substitute them in, cancel out the e to the RTs. We're left with this. Does that factor nicely? I think it does, yep. So then r, what would that be? Minus 2, yep. So minus 2, r is equal to 2 with a multiplicity of 2. This means we have repeated roots. So then we'd use either shortcut method or reduction of order, right? Remember reduction of orders? But I'm going to use shortcut for this because it doesn't ask for reduction of order. Plus, this is a pretty simple case to use the shortcut for, right? So now let's look at this. So then we have r equals 2 twice. So then our y sub h would be c1 e to the 2t plus c2, and we just multiply it by a t. That's the shortcut. Or we can go through reduction of order to get that t, right? That's our y sub h. Our y sub p, step 2, where g of t is all of that. Let me, here, I'll do this. So we can see, right? Oops, did not mean to do that. Okay, so y sub p, this is our g of t right here, would be equal to, so we have a 3. But typically a 3 by alone would be an a, but if you notice, this term right here, this whole thing would be a, if you remember, let's go back up, or t squared plus 3 would also be a second degree polynomial. So in this case, we can group the two together and make them a first degree polynomial. So this by itself, sorry, second degree, because we have t squared, right? So that's a plus a1t plus a2t plus, remember, doesn't matter if we have a subtraction sign, a first degree polynomial times e to the 2t plus let me go to the next line, plus ABC e to the 2t cosine of t, and a sine has to go with the cosine, so d e to the 2t sine of t, right? This is our particular solution. Now we only have two more solutions. Two more examples. So this would be example 5. Also, the 6 examples. Okay, example 5. We have, first step, solve the homogeneous equation. So set it equal to 0. Propose y equals e to the RT. Cancel out the e to the RTs. R squared plus 3r equals 0. Pull out an r. R is equal to 0. R is equal to negative 3. Very nice, straightforward. Come up here, y sub h would be c1 e to the negative 3t plus c2 e to the 0. That's 1, so plus c2. Right? Step 2. Propose our y sub p, where g of t, I'll write it out this time, 3 plus 4t squared plus t squared e to the negative 3t plus sine of 3t. Okay. Oh, this one's pretty similar to the last one. Right here, first degree polynomial. A plus a1, sorry, second degree, right? A, because it's t squared. Okay. Plus, we have a t squared e to the negative 3t. So another second degree times e to the negative 3t. And then we just have a sine of 3t. So plus c sine of 3t plus d cosine of 3t. Oh, did I forget to check for the last one? If anyone caught that, we have a 1 here, e to the 2t, this, and this. Do any of those match? This one does. I can't believe I forgot that, right? I didn't check my solution. So this times t. Now does this match anything up there? It matches that, right? So multiply another t, so that becomes t squared. So now this is the final answer for this one. Sorry I missed that. I completely forgot. Did I do it for the last one? Yep, I did it for that one. Okay, let me just make sure that's... I forgot to check that one. Let me see. Where's my solution here? I think I'm on the wrong one. Oh, here it is. T squared times b. Yep, perfect. We have it correct. Okay, this one. Do any of these terms match any of the ones up here? They do, right? Where's my... I'm just trying to find my solution for this one. What is this one? 3 plus 4. Okay, here it is. Yep. So, do any of these match? I believe 2 of them do. These two don't. We don't have any sine or cosines up there. But we do have a 1. This matches with this, and this matches with this. So, this means... Hold on. We add a t here and a t here. Now, do any of these match any of those? This one doesn't, and this one doesn't, so this is it. This is our final solution. Well, not our final solution, but our final particular solution. Okay, one more example. Or is there 2 more? Oh, this is the last one, example 6. Okay, so, example 6. Homogeneous equation. Plug in. We proposed e to the RT, and we canceled the e to the RTs. We're left with This one's interesting. How do I want to do this? I guess we can divide by 4. Yeah, and then I would just go right ahead and use not quotient rule. What am I thinking of? Quadratic formula, right? So then this would be -1 plus or minus the square root of 1 minus 4 times a times c over a times 2, which is just 2. So r is equal to -1/2 fractions plus or minus 1 minus, those 4 cancels. 1 minus 1 is 0. That whole term just goes away. Right, to see how that works, these 4's cancel. Bam, 1 minus 1 is 0. All we have is this. Okay, so we have what? Repeated root. So we have r is equal to -1/2 multiplicity of 2. So then we propose y sub h is c1 e to the -1/2 t plus c2. We multiply it by that extra t. That's our little shortcut. Or we could have used reduction of order to get that term, right? So now our y sub p, step 2, y sub p is equal to what? Well, we have a 2t e to the minus t over 2, so that is a first degree polynomial times e to the -1/2 t plus b e to the -1/2 t times sine of t plus c e to the -1/2 t cosine of t. Oops. Are we good? Okay, yep. Let's just check. Is this, remember we group those together, or this, the same, as, I believe so, right? These don't match anything, but this does. So let's multiply it by a t. Now does that match anything up here? Doesn't match that one. It matches this one, t squared. Does this match anything up there? Nope. This would be our final answer. Now let me just check this. T squared a1, yep, plus b, yep, plus c, yep. Okay, so we got that one right. So now this was just a bunch of extreme cases of guessing. Whenever you have to actually solve for the coefficients, they're usually not this bad. You usually don't have this many coefficients. This would be very ugly to solve. Especially the one we had when it went all the way up to f, right? That would be really, really annoying to solve. That would be multiple pages of algebra. But anyways, in the next video, we're going to take this y of p, and we're going to learn how to solve for a, b, and c, and whatever else we have. Right? So this video just covered a bunch of different methods of guessing. I'm pretty sure I covered every method pretty much. I might have missed one. I think I got them all. I have never seen any other cases, but if there is any, I would be surprised. Okay, I'll see you in the next video in part 2.